Yeah, thank you very much for this very nice introduction. And today I will cover the proof theory of Peano Arithmetic for a system which is basically equivalent. So I speak about the proof theoretic analysis of a system which is a slight extension of Peano Arithmetic, namely I add function symbols for all primitive recursive functions. This is a system which is basically equivalent to Peano Arithmetic, the conservative extension. Now, for this, I define a set of function symbols. Yes, but what is now?
好了好了，这回可以了，这回可以了，可以了 ，OK。
It's not okay. Okay, then I will continue. So after this short intermezzo, we now continue with this proof theoretic analysis of a slight extension of Peano Arithmetic, and the slight extension is just instead of 0, 1, plus, and times, we have some more function symbols, namely the function symbols for primitive recursive functions. So what are those? Well, I have a function symbol for the successor function. It's a unary function. Then I have the function symbol for the n-ary zero function, constant zero function. I have a function symbol for the projection functions, mapping an n-tuple on the ith coordinate. So PRN means primitive recursive function symbol of RTN. Now, if I have a function h, which is of RTM, and if I have functions G1 to Gm of RTN, then I can compose these functions, and the function symbol for this is H composed with G1 to Gm. Finally, given two primitive recursive functions, I want to define a function which can be defined by recursion. So assume that G is a function symbol of RTN. H is a function symbol, primitive recursive function symbol of RTN plus 2. Then I have a function symbol rec GH. This will be a function symbol of RTN plus 1. And the list of all function symbols is the set PR, which is the union over all PRN, n from 1 or 0, does not matter, the union over all these function symbols. Now, this is the set of function symbols which I use in my system. And then I have a language L0. And this is just consisting of function symbols. And as a relation symbol, we have only the quality. So let me write it like this, and just denote the set of function symbols as language L0. Now, I take a variable or unary predicate extension. This is a predicate symbol standing for an arbitrary relation. And the language of Z is L0 union this variable capital X, or this predicate symbol. And what is the idea here? The idea here is that I want to speak about well orderings. Well orderings are second order properties. One quantifies about non-empty subsets. And to express this in the language of arithmetic, I need an external new function, a new relation symbol, and this is for X. That's the role of X. Now, I can go over and define the formulas. Now, this is the same as usual in predicate logic. So we have equations with equations between terms s and t. If t is a term and x is a new predicate symbol, then x of t is a formula, and for the t is a formula. These are the atomic or prime formulas. And if a and b are formulas, then the implication from a to b is a formula. And if a is a formula, a index a is a formula, such that x is not in the bound variables of AA, then for all x, a of x is a formula. Okay, something similar we have seen yesterday. Now, what are the axioms of Z? Well, we have the usual logical axioms. I will not recall those ones. So the non-logical axioms of Z are the following. Well, I have some axioms stating that successors are never equal to 0. Recall the negation is defined using arrow and falsum. The successor function is 1-to-1. So if s of x is equal to s of y, then x is equal to y. And then we have the defining equations for our primitive recursive function symbols. So we have for all x. Now this stands now for all x1 to xn. For all x, 0n of x is 0. Well, 0 is an abbreviation for the constant 0 function of LT0. This is the normal 0. It's a constant in our system. Then we have the defining equation for the projection function. And if I have a vector x1 to xn, then the value is the ith coordinate. Now, what is the idea here with the composition function? Well, for all vectors of length n, we have h composed with g1 to gm. That's a function symbol which applies to x and is calculated as follows. First, I calculate g1 of x. Then I calculate g2 of x up to gm of x. This is an m tuple. And to this, I apply function symbol h. And finally, we have the defining equation for the primitive recursion. So for all x, if you have a rec gh, then we do recursion, let's say, in the first argument. So this function symbol applied to 0x gives g of x, the start of the recursion. And moreover, if here is a non-zero argument, so if here is a successor of y and x, this is the same as h of y here's the primitive recursion applied to the successor of y and x. Here I use a previously at position y. Okay, these are the axioms. Now, this system Z is a conservative extension of the Peano axioms, and Z is able to speak about discrete mathematics. Z allows for coding and for developing standard discrete mathematics. Now we make some assumptions about coding of natural numbers. So we want to have identification between that the natural numbers are isomorphic with Cartesian products of natural numbers. So for simplicity, we assume that we have available a bijection between finite sequences of natural numbers and natural numbers. And we have a coding function such as the empty sequence get code 0. That if one has coding of, let's say, n+1 numbers, this is a good number of it, then the ith coordinate is smaller than this coding. And we want to have that for fixed n, the function a1 to an going to the code of the sequence is primitive recursive. So being primitive recursive means I have a function symbol for it in the class PR, and the function symbol evaluates according to these laws defined in the axioms of Z. Now, given this, let R be an L0 formula. So a formula where the variable, the unary predicate capital X does not show up. Then assume the three variables of R are given by two variables A and B. Then I say S is smaller than T is by definition the same as R, and I plug in here terms S and T for A and B. That's a definable binary relation. Now I develop some notation speaking about when is this relation a well-founded relation. So I define what is the progressivity of a formula F. It's the following. I want to show f of x. And for this, I want to have the premise of an induction. So if for all y smaller than x, f of y holds, then f of x. This is the premise of induction, and this is the progressiveness formula. Now, the transfinite induction with respect to this ordering found here up to term t is given by the following formula, namely we take the progressiveness with respect to f, and then we obtain in conclusion for all x smaller than t, f of x. Now what's the point here? We have here this unary predicate x, and this may show up in f. So f here is an L of Z formula. And since we say nothing about x, in the standard model, x can be interpreted as an arbitrary subset of natural numbers. So this is a formalization of the second order property, namely the transfinite induction. And the full transfinite induction is the following formula, namely From the progressiveness of f, I conclude for all x, f of x. Now, the next goal is to prove transfinite induction for initial segments of epsilon 0. For this, I have to define what this means. So I will give a concrete definition of an ordering, which is primitive recursive. And then I will show for this ordering the transfinite induction for all t which are an element of this ordering. So for all initial segments, I will show the transfinite induction. Now for this, I use exposition by Wilfried Buchholz, which is very compact. And yeah, the definition is as follows. First, we define a superrelation. So we assume A is a finite sequence. What does this mean? A is a Gödel number of a finite sequence with entries A0 to N. B is a Gödel number of a finite sequence A0 to Bm. Now I say A is smaller than B. Smaller prime B, if and only if. There are two cases. So the idea is we want to compare these tuples lexicographically. So one case is the sequence A is a strict subsequence of the sequence B. So A has the form B0 to Bk. And K is strictly smaller than M. In this case, A is smaller than B. Or we have that the sequences are compared lexicographically. So A starts with B0 to Bk minus 1. And then comes AK until AN. And AK is smaller than BK with respect to the less than prime relation. Okay, this is a ordering. The question is this well ordering? The answer is no. So 1 will be bigger than 0, 1, will be bigger than 0, 0, 1. And so this is not a well ordering. So what is the idea? The idea is to use this ordering as a super ordering of epsilon 0 to single out a subsystem of finite sequences on which this ordering is a well ordering. Now, lexicographic orderings have the property that they are linearly ordered, all transitive. So the first lemma is this ordering less than is transitive. So if x is less than prime y and y is less than prime z, then x is less than prime z. This I will not prove, this is just a lemma. Now, having this ordering, I define a set of sequences OT. Now, this is defined inductively. First clause is 0 is in OT. This will be the minimum of the ordering. And if a 0 to an are in OT, and if what an is less than equal prime an minus 1, less than equal prime, less than equal prime a0, then the sequence a0 to an is in OT. And the last definition is A is less than B if and only if A and B are in OT and A is less than prime B. Now one can show that the characteristic function of OT is primitive recursive, so OT is a primitive recursive set of numbers, and the less than relation is a primitive recursive relation in this set. So OT and less than form a primitive recursive set of notations together with an ordering, the primitive recursive ordering. Now what I need to is a concatenation function. So with A0 to A M star V0 to Bn, I denote the following sequence. The result is we start with A0, going up to AM, and then the next entry in the sequence will be B0 and then Bn. So if I take two sequences, I just put them after each other, and then I calculate the corresponding Gödel. Now, what's the first goal of today is to prove the transfinite induction for all initial segments of this ordering in the set. For this comes the crucial definition, and I switch now to a new color because it's an important definition. So if I have a formula in LZ, F bar of Y is what? Well, it's a statement for all X. Now we have the premise of a transfinite induction. So for all Z smaller than X, F of Z, this implies that I can extend this premise of transfinite induction to for all Z smaller than X, concatenated with the sequence of length 1 consisting of this one. And from the higher standpoint, the proof of transfinite induction for initial segments of epsilon 0 in Z just requires this formula. When you can remember this formula, the rest works by itself. Now, this is a bit of a high-level argument, so let's see how it goes. So we have the first lemma. Well, it's of course not so simple. So we claim in our formal system, we can prove the following implication. From the progressiveness of arbitrary formula F, we can conclude the progressiveness of F bar. How to prove this? Well, this is a complex formula. So proof. Of course, I will not write down a proof. I will give an informal argument. So informal argument is I basically work in a model of the theory, and then I do the usual informal argumentation. So assume the premise. So the premise is 1. What is to show? this formula. Okay. Now, I have to show basically the premise of a transfer induction. So assume, therefore, what for y less than b, f bar of y to show is what f bar of b. So I have to show it in quantified version. So I take a variable for the arbitrary element. So I assume this one, and I have to show f bar of b. Now, what I'm doing is I take an arbitrary element a, and I assume this one for a. So assume all z smaller than a, f of a to show is this one here for all z smaller than a times yeah, this b over here, f of z. Now, how to prove this? The claim is the following. For all n, for all y1 to yn smaller than b, we have for all z smaller than a times y1 to yn f of z. Now, first of all, how to read this? This is not yet so clear because this is not a formula in the language of our formal system. But we can read this basically as a statement about one single quantifier quantifying about sequences of length n, where n is given here. Now we prove this by induction on n. Okay, now assume that n is equal to 0, and this is empty. But if this is an empty sequence, a star, an empty sequence is a, then we see for all z smaller than a, f of z is true by assumption 3. Now, assume this is true. So, induction step. So, assume for all z smaller than a star y1, yn, f of z. Now, assume yn plus 1 is smaller than b. and assume also that the y1 to yn are also smaller than b. Now we check 2. For all y less than b, f bar of y. And for this x, I take a star y1 to yn. So then, by assertion 2, we have for all z smaller than a star y1 to yn plus 1, f of z. So this means claim 4 is shown. Now we have to show this one. For all z smaller than a star b, f of z. How to prove this? Well, just pick an element smaller than a star b. Let C be an element smaller than a star connected with singleton B. I have to go into the definition of the ordering. So there are two cases. It could be that C is already smaller than A. But then I have assertion 3. Then I have f of C. That's fine. Otherwise, C starts with sequence A, and then comes some rest, which is smaller than B. Otherwise, C has a form A star, and here I have a sequence B0 to Bm, where B1 to Bm are smaller than B. Now, in this situation, we can apply assertion 4. And obtain what? For all z smaller than C, f of z. So for all z smaller than A star B1 to N, f of z. Now we don't want to prove that one. We want to prove f of c, but we have proposition assertion 1. Proposition 1 is the progressiveness. Here is the premise. So by 1, we obtain f of c. So you see the proof fits nicely together. You just do it step by step. If you have written down this formula f bar, it follows more or less automatically by some case distinction. More or less, of course, you have to fill in the details. Now the next lemma is interesting because we show what? Assume that we have the transfinite induction over f bar and a. Then, so that proves the transfinite induction over f, and here is a singleton sequence 1. Now, one is, of course, to put it with some semantics. Y stands for an ordinal, and the sequence of length 1 with entry y stands for, so if y stands for alpha, the sequence with singleton length, singleton sequence with entry y stands for omega to the alpha. Now, what does this mean? If you want to prove induction for long ordering about a function, about a formula f, it suffices to have a short transfinite induction over a formula f bar, which is more complicated than f. So basically, you can jump in the ordering 1 omega power higher by using a transfinite induction for an ordering which is shorter, but which has one more quantifier. Okay, proof. Well, let's assume this one. Yeah, claim is to show transfinite induction over f singleton sequence with y. Now, for proving the transfinite induction, we can assume the progressiveness. So this is assertion 1. To assume that I have the progressiveness over f. And then I have to show induction over for all x less than singleton y, single sequence y, and then the f. Now, with the previous lemma, we can obtain the progressiveness of f bar. Now we have here the transfinite induction for f bar and y is true. We have the progressiveness of f bar. So by 1, we can conclude for all z smaller than y, f bar of z. Now I have here the progressiveness of f bar. Here is the begin of a transfinite induction. So by 3, call this assumption 3. 3 implies then f bar of y. Now we look what this means. And what we do is we have here f bar of y. That's good. Now for x, I plug in a specific value, namely number 0. Then there are no z smaller than x. And then the conclusion is for all z smaller than singleton y, f of z. So then for all z smaller than singleton y, f of z. Now this is shown, right? This shows this formula because from the progressiveness of f, we conclude for all z smaller than singleton sequence y, f of z. This is precisely this formula. Okay. And the final theorem is what? Let A be a term in OT. Then Z proves the transfinite induction of an arbitrary formula F for the along the predecessors of A. Proof? Proof is now very easy. So I define a sequence which is cofinal in our system. So C0 is just 0. Cm plus 1 is, I take Cm and then the singleton sequence of Cm. And then one can show by some induction for a given A in OT, there is some M such that A is smaller than Cm. Now this M can be constructed effectively. We can just use the number A. A is smaller, not with respect to the usual ordering, but with respect to the ordering of OT. And if you have transfinite induction up to Cm, then of course for all shorter orderings too. Now by induction on M, we show transfinite induction over F and Cm. Clearly, we have transfinite induction over F and C0 because for all x smaller than 0, f of x, this is vacuously true because there are no elements smaller than 0. Induction hypothesis says we have transfinite induction for Cm, but we have transfinite induction for arbitrary formulas, and now we don't choose formula F, we choose the formula F bar. And that's the trick. Because now we can use our previous lemma. And this then implies transfinite induction over F, Cm plus 1. Now this is a proof by induction on M, but this is an auto-induction over standard natural numbers m. Okay, now that's a bit of a mysterious proof. Now we want to see how this can be visualized. But this is a purely combinatorial proof. It is a sense of the argument given by Gensen. Yeah. So now I come to the ordinals below epsilon 0. And of course, the problem is now to figure out how to speak about ordinals without explaining what they are really. So what I'm doing is I give a sort of alternative description. So let E be the least set of unary functions such that first, the constant function C0 is in E, where C0 of x is equal to x. And second, if G and H are in E, then we have the function x maps to x to the G of x plus H of x is in E. And for functions in E, we say f is smaller than G, if and only if there is a k such that for all L is as big as k, we have f of L is smaller than P. Now, this is interesting. One can show this is a linear order. And in fact, this set E with this ordering is isomorphic with our set OT. So every F in E, F is different from the 0 term. Every F can be written as F, well, some notation. So omega to the F defines the function x to the f of x. And then f can be written uniquely as omega to f1 plus omega to fn for some f1 to fn in E, which are weakly decreasing. With respect to this ordering, and I write f plus g for the function which is defined by pointwise addition. So here I write then this notation for the sum. Now I define a mapping O from finite sequences into E. As follows. O of 0 becomes T0, and O of A1 to AN becomes omega to O of A1 plus omega to O of AN. Okay, now what one can prove is theorem. Okay, if A is in OT, then clearly O of A is an element in E. One can show if one has this relation on the notation system, then one gets the following majorization for the functions in E. And finally, for every function in E, there is an A in OT such that O of A is equal to F. So what does this mean? This means O is surjective on E. This means O is order preserving. In particular, O is 1-to-1. And O is an isomorphism between order isomorphism between OT and less n and function class E with the less n relation. Now the function class E and F visualizes the ordinals in a nice way. So we have if CK is a constant function with value k, then we have C0 is the smallest ordinal, smaller than C1, smaller than C2, smaller, and then comes the first limit ordinal, which is omega to the 1, which is identity. It's smaller than identity plus 1, smaller identity plus 2. We get the second limit point, which is identity plus identity, which is omega plus omega in our system. And we can continue. We can form omega times omega, which is identity times identity. We can form identity to the identity, which is omega to the omega. And this is smaller than omega of identity to the identity to the identity. And we can iterate, and then we see the iterated exponential powers are cofinal in E. And this gives a nice bijection between the formal system OT and this nice function class E. And to see how the ordering works can be best visualized by looking at E and not looking too much on the formal system OT. Now we have it 5 minutes past 11. So maybe it's now a good moment for a break. So what will part I showed transfinite induction for all initial segments of epsilon 0. And the second part, I will cover the unprovability of the transfinite induction when you look at the full segment of notations, which also can be used to study the provably recursive functions. So I suggest now a 5 minutes break, and then I will continue. Very good. So in the next lesson, we will see the unprovability of epsilon 0, and also that the Hardy function of level epsilon 0 is not provably total in the system Z. Now, what are the Hardy functions? It's the following definition. So is defined in the following. H0 of x is just the identity function. Then we take an element in E, or alpha. H alpha plus 1 of x is, well, in defining H alpha, I assume that H alpha plus, in defining H alpha plus 1, I assume that H alpha is defined and applied to argument x plus 1. And if lambda is not a successor, so lambda is a limit, H lambda of x is H lambda of x and again x plus 1. Now there are certain undefined notions. What is lambda of x? Well, if we assume for this the following, namely lambda can have two shapes. Lambda can have the form omega to the alpha 1 plus omega to the alpha n. And here's the successor alpha n plus 1, where alpha 1 is at least as big as alpha n plus 1. In this case, lambda x is defined as omega to the alpha 1 plus omega to the alpha n times x. And this is canonically converging to this term here. It's can be easily verified for the members of E. And if lambda has the form omega to the alpha 1 plus omega alpha n, and alpha n is also not a successor, so a limit, then lambda x is defined as omega to the alpha 1 plus omega, and then I assume by induction that alpha n will be smaller than lambda, but I've defined alpha n of x, and then this is the canonical definition. Now, these are the Hardy functions, and what is the goal of the talk today? Well, first, let me continue with what is the Hardy function of level epsilon 0. For this, I have the index E. This is given by h omega x of x, where omega 1 is omega n plus 1 is omega to the omega index n. So an iterated exponential power. And what is the goal? The goal is to show that h e of x is not, h e is not a provably total function in arithmetic. So we have our first theorem. The first theorem says formal system Z proves, so if we have a function on an alpha in or t or an e, then Z proves for all x there exists y, h alpha of x is equal to y. So Z proves the totality of the Hardy function of level alpha, where alpha is an element in OT or alpha is in E. Now this is sort of routine, but still it's not so clear how to formalize this. So we have to write down what does this formula mean. Write down a formula h a x y z, and z codifies the computation tree for calculating h alpha at argument x giving value y. So what does this mean? This stands for what? Z is a sequence number, a long sequence consisting of sequences of length 3. I don't get this. So Z index I is the decoding of sequence Z at place I. And Zi is a sequence, and the length of Zi is 3. Now, the idea is we want to these sequences of length 3, they codify certain values of the Hardy function. So let's consider the case. What does it mean when we start with 0? Well, then I want to have that we are in the first case where h0 of x is equal to x. So if I is 0, then I want to have, well, there is a function value, but I don't know the function value. So there will be a v less than equal to z. And z0 consists of a triple 0 v v. So this means the first triple codifies h0 of v is equal to v. Now, could be that we are in the end of the sequence. Now, a sequence Z consists of Z0 up to Z index length of Z minus 1. So that's the reason why I'm at the end of the sequence, I have length of Z minus 1. Then I want to have that Zi as a form, a triple consisting of A, X, and Y. So at the end of the calculation, I want to have that HA of X is equal to Y. And now I have to figure out what happens in between. So if I plus 1 is equal to the length of Z minus 1, now I have to formalize these two steps. And well, for technical reason, I unify these two clauses by claiming that the fundamental sequence for alpha plus 1 of x is equal to alpha. Then both cases come down that I'm jumped from alpha to alpha in brackets x. So they can be unified into one clause. Now, we take a quantifier, b, e, w less than equal to z. If at position I plus 1, we have what? B v w. Then at position before, we had that B was evaluated at V. The X becomes 5 plus 1, and the W remains the same. So what does this codify? H lambda of X is equal to Y, the same as H lambda X of X plus 1 is equal to Y. So this is B stands for lambda. Here is lambda, here is lambda V. Here is X, here is X plus 1, and here is a function value. So this means the sequences are locally correct according to this system of defining equations. Now I define the formula HA of X equal to Y. This is the formula. There exists a Z such that HA X Y Z. And this formula here describes this formula over here. Now, by induction on A, with respect to the O-ring on orientation system, I can now prove for all x, there is a y, h, a, h, h, a of x is equal to y. So this is by induction on A. So how do I prove it? Well, let x be given. Now, by induction hypothesis, I can assume that I can calculate h a of x. So there exists a z prime for h a of x, or maybe I write it in this way, h a of x. Induction hypothesis applies to smaller a, but for all x. For x, I now use x plus 1, and I obtain a z prime. Now this codifies the calculation of h alpha x. I get a sequence of calculations where the last entry is given by these elements. Now I have to define what is the new z. Z will be z prime extended by elements a, x, and y. So the calculation tree has now been extended. So I have a calculation tree for this element here. And now I make it one longer to obtain a computation tree for this value. Now, if I have this z, one can verify if this is true, and z has this property, then we have h, a of x, y, and z. And that is what we have to prove. So what does this mean? This means in our formal system, once we have transfer induction available, we can prove the totality of the Hardy function of level alpha, where alpha is in our system of notations. Now, what is the goal of today? Z does not prove for all x there is a y, h e of x is equal to y. Now, h e of x is defined by this clause, and one can easily define the computability predicate also for this equation. Now, what does this show? Z is not able to prove the transfinite induction over the full notation system OT. Why it is the case? Because if Z would prove transfinite induction over full of E, I could use this proof to prove the totality of the Hardy function of level E. But we are going to show this one. This one has, in particular, as a consequence, this theorem. Okay, and now a completely new story will start, namely, I will work on this goal. And this proof is based on cut elimination. So, how is this possible? Well, we do cut elimination for a system of arithmetic, and we know in the formal system of arithmetic we cannot do cut elimination. Therefore, we make a transition. We go from the finitary system Z into a transfinite extension, which looks more complicated, but it has certain features, namely that the scheme of complete induction can be proved by a given infinitary rule, the so-called omega rule. Cut elimination is even easier than for Peano arithmetic. And then we analyze the cut-free proofs to get our intended results. So, what is the language? Well, we have only primitive recursive function symbols. And for our purpose, the unary predicate x is no longer important, so I just forget about this. Now, the formulas are not formulas in the usual sense, because I only consider closed formulas. So no free variables. The free variables are needed for the universal quantifier, for the introduction of a universal quantifier in the succeeding. But for this, we use the omega rule, and so we can get rid of this. Now, every closed formula can be evaluated. So in the closed formula, they are showing up terms, closed terms for primitive recursive terms. And there's a standard semantics to evaluate these closed terms. So they have a definite truth value. So by true, I denote the true atomic formulas. True atomic formulas. And false is consisting of the false atomic formulas. So I was a bit general, too general. So I'm speaking about that atomic formulas have a truth value and they can be evaluated. And this is just a notation. Now I also work with an operator. So what is an operator? The function from n to n, fulfilling two properties, namely it is weakly monotone and secondly, we have the property f of m is at least as big as n. So it's also called inflationary or whatsoever. And given an operator, I define a new operator, f in brackets I. A very simple modification. It's fi of m is f applied to the maximum of I and m. Now it's somehow important to work with the right definition. One could also say, well, I take sum of I plus m, but this is in our context not good. One has to work precisely with this definition, otherwise we will be punished at a later moment. Further, I have a norm function for elements in E. The complexity of omega to the alpha plus beta is given by 1 plus complexity of alpha plus the complexity of beta. Now, this is a sort of complexity measure, the length of an ordinal. And next, we have a definition of calculus. We define f derives a sequent gamma delta with height bounded by alpha and cut ring bounded by r. this holds if a certain condition holds, namely the complexity of alpha is bounded by f of 0. Why we do so is not yet clear, but somehow the function f could control the information. So this derivation of gamma double dot delta is a derivation in sequent calculus. F, the role of f will be made clear in a moment. Alpha stands for the height of the derivation, and R is a strict upper bound for the complexity of all cut formulas showing up in this derivation. Okay, now what are the axioms? The axioms are somehow easier than in standard classical predicate logic. So what are the axioms? Well, if gamma would contains one false formula, remember gamma double dot delta means from the conjunction of gamma I can conclude the disjunction. Yeah. Okay, so if gamma contains a false formula, then this should be derivable. If delta contains a true formula, it should also be derivable because the disjunction if the disjunction contains one true formula, the disjunction should hold true. So if gamma contains a false formula or delta contains a true formula, then we have derived an axiom. Now we have the rules for arrow introduction in the succeedent. So assume if f derives with an ordinal alpha 0 and r, gamma, comma, p double dot c, comma, delta, and alpha 0 is smaller than alpha, and if the formula p implies c is an element in delta, then I can derive gamma delta as before. Or another clause is the error introduction in the antecedent. So we have derived f alpha 0 r gamma double dot p delta, and f derives gamma comma c double dot delta alpha 1 and r. Alpha 0 and alpha 1 are smaller than alpha. And the formula P implies C is an element in gamma. So this formulation of the sequent calculus is slightly different from the version I used before. Here I somehow smuggle in the principal formula in the via this clause that is directly contained in gamma. So it's in this formulation, the formula which we are deriving is always part of the premise. In the other calculus, we had some more freedom. But this does not matter so much. Now, until now, the role of f is completely unclear. We haven't used it at all. Now, at some moment, the role of f should become clear. So we have universal introduction in the antecedent. Now, the universal introduction in antecedent is basically the introduction of an existential quantifier where one has a witness. So we have f proofs with some alpha 0 and r, gamma, comma, and now there are certain choices. Either I use a closed term, or I just use a numeral k. This is equivalent. K should be the value of this closed term. But it suffices now to work just with numerals, for terms which are built up using 0 and successor. And alpha 0 is smaller than alpha. The formula for all x, f is maybe not good, because here's an f. So I use here phi, let's say, for all x phi of x. This is assumed in gamma. Now, the trick in this formulation is I make an additional assumption, namely witness control. And remember, in the proof of predicate logic, when you do a Wall theorem, you collect your existential witnesses from your cut-free derivation. We do something similar. We demand that k is less than or equal to f of 0. So here is a role of f. The first coordinate controls the existential witness. Now there's a rule for all introduction succeedant. So we have for all I derivations of gamma, delta, phi of I. The alpha I are all smaller than alpha. And we have for all x, phi of x is the formula in delta. That is the famous omega rule. If you can derive phi of I for all natural numbers I, then I'm allowed to derive for all x, phi of x. Now, it's important to note here that one has infinitely many premises. And this allows to model our universal quantifier, but it allows a bit more. And for the bounding function, I now use not operator f, but the modified operator f in brackets I. So it's a bit weakening in the assumption. And these are the two places where the operator f is used. Maybe the third place is over here, which I should also put into red. And what remains is the cut rule. And the cut rule, well, is as usual. So I will write it in the remaining part over here. So we have alpha 0 and r, gamma phi, double dot delta, alpha 1 is an r, becomes an r, gamma double dot delta phi, and alpha 0, alpha 1 are smaller than alpha, and the cut formula phi as complexity 3 is smaller than r. So that is the role of the number r in the proof, but we have seen this already in the treatment of Genson's result. Okay, now this is calculus which I invented some years ago, which allows for a smooth characterization of the provably total functions. Now the first thing is we want to have a weakening theorem, lemma, but this is easy. So what's going to happen if gamma is extended to gamma prime? delta is extended to delta prime, if alpha is extended to alpha prime, if r is less than or equal to r prime, if pointwise f of L is less than or equal to g of L for all L, and if we have that the norm of alpha prime is less than or equal to g of 0, then we can conclude we have made everything bigger. And it's no surprise that we obtain g alpha prime, r prime, gamma prime, double dot delta prime. There's an easy induction on alpha, which I will not give. Now, for cut elimination for predicate logic, we needed some sort of substitution lemma. That is not needed here. We directly go to the inversion. And this is interesting. Now, the inversion comes with several parts. Most of them are easy. So the first one is what? If you have a false formula in the succeedent, we can delete it. So if f derives gamma delta p and p is false, then you can just leave it out. So there's no rule where a false formula is a principal formula on the right-hand side. Symmetrically, we have can delete true formulas on the left-hand side. Then we have inversion lemma for the implication. Now we have two of them. So if f derives with alpha r, gamma, delta, and now we have here in the succeedent implication phi implies psi. And we can derive with f alpha r, gamma phi double dot gamma psi. We have also an inversion lemma for the implication in the antecedent. And the conclusion is that we get two statements. Namely, one is that we obtain the formula phi in the succeedent. And the other one is the formula psi in the antecedent. Okay, that's fine. And now the crucial point, what is really crucial for cut elimination is the inversion of the universal quantifier. So if f derives with alpha and r, gamma double dot delta for all x phi, then we can derive with alpha and r, gamma double dot delta, and here we have phi of I, an arbitrary I. But now we have to look back. What can we expect? We have here for all introduction in the succeedent. And it's not, that's the control operator is f, but it's f of I. This is used over here. We have to invert on f of I. Okay. All these lemmatas are proved by induction on alpha. and they are basically routine. Not really. It's very important to look at the proof of 5. So the critical case is last rule was universal introduction in the succeed. So what's going to happen? Now it's somewhat very tricky. So we have the premise, namely for all j, we have f of j, f in square brackets, j proves gamma delta phi of j, and the formula for all x phi of x is shown up in the right hand side. Okay, this is a premise for our universal introduction. Now what this means is we now jump onto position I is equal to j. So we get here I and here I. Now we apply the induction hypothesis to this situation. But here's alpha I and here's R. Alpha I is smaller than alpha. Induction hypothesis. And now appears something which is rather magical. Therefore I switch colors. I take this operator and I invert this formula to position I. So I have to apply it to I. And obtain gamma delta phi of I, phi of I. Now why is this in red? Because this operator here is the same as f in brackets I. And that is the point where one uses this very specific definition of f square brackets I. If you would use a different version, then this type of quality can easily break down. So it is really important to have this precise definition, and then it becomes idempotent. And of course, on the right-hand side, in the succeeding, I have sets of formulas. So phi I, comma phi I just means phi I. So, and then we are done. But this is the point which I want to stress. If you modify the proof, here is a possible problem for pitfalls. Okay. Now comes the reduction. Notice that the reduction lemma is crucial for the reduction theorem. If you want to lower cut ranks by 1, you first have to prove the reduction lemma. How does it go? Well, we have two situations. We have gamma phi double dot delta and the derivation of gamma double dot phi comma delta. This is controlled with F. This is controlled with G. Here is beta, R, alpha and R. And the rank of phi is less than or equal to R. And I want to conclude basically with alpha plus beta times 2 and R gamma double dot delta. Now what is here the problem? The problem is to find out what is the operator controlling this derivation. So the left-hand side is controlled by G, the right-hand side is controlled by F. So you would say we go to the maximum of G and F, but this is not going to work. So now it comes to the heart of the matter, namely cut, reduction of a cut has to do with composition of boundary functions. So I define an operator, C of F and G. And now it matters, this operation is not fully symmetric. So G comes on the right-hand side. So it's a composition of F with G plus some minor stuff, F plus G, pointwise addition. What's important is this part. So F composed with G. There is the heart of the matter. Now, of course, the question is, what is behind all this? How to prove this? Well, the proof is done by the usual proof, induction on beta. So first of all, why I have this artificial extra plus F plus G? Well, I want to control the norm of this function, the norm of this ordinal. The norm of alpha plus beta times 2 is basically bounded by CFG of 0, because the norm of alpha is bounded by F of 0, and the norm of beta is bounded by G of 0. And this is inflationary, so it's an easy estimate that this is going to hold. Okay. Now, time is getting short, so I just concentrate on the critical case. So we do induction on beta. And in the critical case, we have universal introduction in the antecedents. So what do we have? We have G controls derivation of beta 0 R gamma. Let's assume phi has a form for all x psi of x. And we have here psi of k. Phi double dot delta. Okay, now in this situation, we can apply induction hypothesis. So we get the composition of F and G controls alpha plus beta 0 times 2 R. Induction hypothesis says we can get rid of formula phi. So this is the situation, but now we have to get rid of psi of k. Now we remember from the cut elimination for predicate logic, when we are stuck in doing the induction on this part, we have to go to the other part and do the corresponding inversion. That is what we do here. Phi is the universal formula. And we have here property 5. So we can do the inversion. So inversion gives what? We have f of k proves with alpha and r gamma double dot. Phi is this universal formula. So we have here psi of k comma delta. Now we do a cut over psi of k and we are done. But that's not so clear. What is the point? Clearly f is bounded by this operator. But now the problem is a k, f in brackets k, and k can be as big as 100 factorial. So it could be that this finite number spoils the construction. And now the magical argument is the what? You have to bound f of k in terms of this function. How is this possible? Well, the proof works like this. You have f of k is bounded by, and now it comes. It's important. We have the universal introduction in the antecedent of this witness k. Now we have to use in the universal introduction in the antecedent this Xler condition. K is bounded by operator at position 0. So here we know that k is bounded by g of 0. So pointwise we get here f in brackets g of 0. And then you see here comes the composition. This is bounded by CFG. And this allows us to do the cut. And then we are done. That is nice. And all the other arguments in the proof go through. But this is the crucial point. This inequality is guaranteed by this Xler condition. So it's not only that we collect here existential witnesses just for fun. It is crucially needed in the cut elimination procedure. Now comes the next part. It's, this can be eliminated. Now comes the reduction theorem. Well, so assume if f controls with alpha and r plus 1 derivation gamma delta, then we want to have with omega to the alpha and r, so we reduce cut length by 1 and get here exponential gamma delta. And the question is, when we have here operator control as f, what is the operator control for doing this? Now we know that in the proof of the reduction theorem, we have to use the reduction lemma. Now it could be that we have to apply the reduction lemma alpha many times. So we have to iterate f alpha many times. So it's an obvious idea to say we take here the alpha's iterate of f. Now f is a number theoretic function and alpha is a sort of infinite ordinal. So this is of course not well defined. Now what is f alpha? F alpha of x is therefore defined as the maximum taken over. First we take function f, and then we take our composition operator, composition, along f to gamma, f to delta, where gamma and delta are smaller than here argument x, where gamma and delta are smaller than alpha. Now you say, well, this is also not well defined because I have here maximum, so I need here a finite set, and this set of values is not finite. Now the point is we assume that the norm of gamma and the norm of delta is bounded by x or by f of x. Let's see what I have chosen. F of x. But this is not so important. Now, given an ordinal term, beta, there are only finitely many alpha less than beta having a term complexity bounded by a given number. This is usual observation with if you have terms over signature, if the signature is finite, you have only finitely many terms of a given complexity. So therefore, you have here a finite set of function values for which you can take a maximum, and that's f alpha. Now the proof runs as follows. Namely, we do induction on alpha. That's fine. So assume last case, last applied rule was a cut, where we have f proofs with alpha 0 and r plus 1, gamma phi delta, and same operator f controls with alpha 1, r plus 1, gamma delta phi. Okay, what can we do? We can apply induction hypothesis. So here we come with an alpha 0 iteration, control this omega to the alpha 0 r gamma comma phi delta. And here we have an alpha 1 iteration of f. Now we apply our reduction lemma. This means the composition of f alpha 0 and f alpha 1 controls. So the rank of phi is smaller than r plus 1, which means the rank of phi is less than equal to r. So we have here omega to the alpha 1 plus omega to the alpha 0 times 2. Here is r gamma delta. Now, f alpha is at least as big as composition of f alpha 0 and f alpha 1, because now comes the moment where we use this extra condition that when we derive a sequent with height alpha, that the norm of alpha is controlled by the operator f. So this is a crucial moment. It's the first time where this bounding condition is needed. So here we see the norm of alpha 0 is bounded by f of 0. And here the norm of alpha 1 is bounded by f of 0. So alpha 0 and alpha 1 are smaller than alpha. The norms are under control. Therefore, by definition of f alpha is pointwise majorizing this function. And moreover, we have the critical rule for the exponential function, namely omega to the alpha 0 plus omega to the alpha 1 plus omega to the alpha 0 times 2 is smaller than omega to the alpha. Is easily calculated using the normal rules for exponentiation. And hence we conclude with f alpha we can derive gamma double dot delta. So this is a great argument. It works very well. Now, there's one last critical case, which I did not mention, but which works fine. Namely, the case, the last rule in this derivation was a universal introduction in the succeedent. But this works out. But due to time reasons, I will not cover it. Well, finally, we want to get bounds for provably total functions. So we have an interesting theorem. Namely, if f proves an existential statement, P is quantifier free, and if the proof is cut free. So if you can prove there is an x phi of x, then there will be a k less than or equal to f of 0, such that phi of k is true. And second, if f controls derivation, cut-free derivation of for all x, there is a y, phi xy, by quantifier free, then for all m, there is an n bounded by f of m, such that in the standard model we have phi of m and n. This is interesting because, as I said, we want to exploit cut elimination. So we have to figure out what does cut freeness give. And okay, let's have a look. Proof. So first of all, the formula there is in x phi of x is the formula not for all x not phi of x. This is a specific property of our calculus, which makes life somewhat difficult. But okay, it's not really difficult. So this approach, which I'm presenting, is stable under these sort of things. So we have not for all x not phi of x. So what does this mean? This means, by definition, we have derived this formula. Now we can do inversion, which I wiped out in the meantime. But inversion means basically that we can shift the first part of the implication into the antecedent. And now we do induction on alpha. So how can we derive this sequence? There's only one rule which can be applied. And the rule which we can apply is, the only rule which works is universal introduction into the antecedent. So we have a shorter derivation of the formula for all x not phi of x, where we have witness not phi of k, and k is less than or equal to f of 0. Now there are two cases. Case one, phi of k is true. If phi of k is true, then I found my k less than or equal to f of 0, such that phi of k is true in the standard model. Second case, phi of k is false. Now, if a false formula over here, and by inversion, I can wipe it out. So I get f proves alpha 0 and 0 for all x not phi of x, double dot falsum. And then the induction hypothesis for alpha 0 gives there exists a k less than or equal to f of 0 such that phi of k is true. So that's a very nice argument. And the second case is similar. So assume f controls a derivation of a pi 02 statement. Then we do inversion. Invert on m. So f of m controls then the derivation is alpha 0 of there is an y phi of m and y. Now here we have an existential statement. So by 1 we have there will be a k less than or equal to f m of 0 such that in the standard model we have phi of, call it n maybe, phi of m and n. And f in brackets m applied to 0 is nothing else than f of the maximum of m and 0, so this is m. So for all m, there is an n such that phi of m and n is true. That's the reason why we do cut elimination. So first we have proofs with cuts. Then we reduce the cuts to 0. And if you have a cut-free derivation of a pi 2 statement, then the bounding function which controls the derivation is also bounding this pi 2 dependence. Now I clean the board. Well, the next theorem is the following. Namely, if we have a derivation of a formula phi in the formal system with three variables a1 to ak, then there is an operator, and for simplicity I need to assume that there's a primitive recursive operator f. Why do we have to start with a primitive recursive operator? Because we have function symbols for all primitive recursive functions, and to bound corresponding existential witnesses, we have to start already in the beginning with primitive recursive bounding functions. So there's a primitive recursive operator f. There are numbers p and q smaller than omega, such that f controls such that for all values m1 to mk, we can prove with omega plus p index q phi of m1 to mn. That is the so-called embedding theorem. Now, this requires a certain amount of time. One can do this, but this is a sort of routine argument. The only non-routine argument is the treatment of complete induction. So for proving complete induction, one needs a truly infinite proof. And basically the idea is, well, when you have normal assumption of a complete induction and you want to prove that an assertion is true for number n, then basically you need to prove which has length linear in n. And when you want to prove the formula for all x phi of x, you need to prove which is bigger, length and height bigger than all natural numbers n. So this naturally leads to an ordinal bound which is infinite. And then for the rest, it's just sort of routine. Okay. Now, I assume now that this is going to work. Then we can do the following. Namely, we do our classification of provably recursive functions. So assume we have Z proves a statement for all x, there's a y, phi of xy. What we are going to do is we apply embedding. So we find primitive recursive operator f, finite numbers p and q, such that for all x, there is a y, phi of xy holds. Okay? Now I clean the board. Okay. Now we do cut elimination. So we apply our cut reduction theorem. So with an omega times p plus q iteration, we reduce cut rank by 1 and get here omega to the omega times p plus q. And here we have our formula for all x. There is a y, phi of xy. Now we reduce the cut again. We get here q minus 2. Here's omega to the omega times p plus q is for all x. There's a y, phi of xy. In the meantime, we have to iterate our operator again. So we have operator omega times p plus q. This one has to be iterated omega to the omega times p plus q many times. Okay, now at some moment we hit here number 0. Here we get an omega nested tower, omega times p plus q. Here's our formula for all x. There is a y, phi of xy. On the left-hand side, we get the complex operator, namely f omega times p plus q. Then we get omega to the omega times p plus q. And then we get a nested tower of iterations. And here we have an omega power of 1 height less. Here's omega times p plus q. Now call this operator here g. Then finally we have, and call this ordinal alpha. And we have g derives with alpha and 0. For all x, there is a y, phi of x0. Now we apply our lemma or theorem from just ago. This means for all natural numbers m, there's a number n such that n is bounded by g of m. And in the standard model, we have validity of phi and m and n. Okay, so this is the classification of the provably recursive functions using complex iterations. But I promised a bit more. I promised to use to prove something about the Hardy functions. Now we have to find a lemma which shows that these nested iterations can be modeled by the Hardy function. Now the lemma is the following: if f is controlled by h alpha, which means pointwise majorization, or let's call it beta, then f alpha times iterated is bounded by h omega to the alpha plus beta plus 1 plus 8. So this lemma allows step-by-step bounding these nested compositions by Hardy functions. So if you apply this lemma finitely many times, we see that for G, there is a beta in E such that G of L is bounded by H beta of L for all L. So this means if we have a pi02 statement provable in formal system Z, then this pi2 statement is controlled by a function H beta, where beta is in E. Now finally, assume what? Z proves for all x there is a y, H E of x is equal to y. We want to prove that this is impossible. Now we have seen before how to write down this formula. So this is basically, there exists a computation tree verifying this. Then you have here two existential quantifiers. You can move them into one existential quantifier. I will not be too explicit here, but assume that Z is possible, then by our theorem, which we proved already, then there is alpha in E such that for all M, there is an N such that H E of there is an alpha such that for all M, there is an N less than equal to H alpha of M such that H E of M is equal to N. So what this means is basically that H E would be dominated by a fixed H alpha. Now H E stands for the tower of exponentials of unbounded height. Alpha is dominated by a tower of exponential by a finite height. So an easy induction or easy verification shows that this is impossible. So this is basically the proof that the upshot is final theorem of today. Z does not prove for all x there is y, H E of x is equal to y, and E stands as a codification of epsilon 0. So the totality of the Hardy function of level epsilon 0 is independent of the formal system Z. And that's our first example of concrete incompleteness result for Peano Arithmetic, where the system Z is stronger than PA. PA has only function limits for plus and times. So, of course, it follows easily that PA does not prove for all x there is y, h, e of x is equal to y. So we have here our first natural and concrete incompleteness of the formal Z. Moreover, Z does not prove the transfinite induction over whole of E, because if it would so, then it would prove the totality of the Hardy function of level epsilon 0, which, as we have seen, is impossible. Okay, that is the moment where I want to stop. Thank you.